Good morning, students. We are resuming our discussion of electric fields. Most of the discussion is now complete, but of course, the practice of the questions remains. So in order to make a few things clearer, I have selected a few questions for discussion today. If needed, we may spend another day practicing similar questions, and only after we are satisfied that now we understand those concepts which are repeated in the past paper questions, we'll move to the next topic. The first question that I have selected for discussion is about how electric field varies with distance, especially if there are two charges placed side by side. This question is quite common in the past papers, so we must understand the typical shape of the graph, what quantities we can calculate with the help of it. So if we repeat these questions again and again, there are very important, simple concepts that we learn in it. And only if we fully understand the idea, we can attempt the past paper questions adequately. There are two charged spheres placed side by side. Let's say we have a sphere placed like this at a certain position in space, and there is another sphere at a certain distance placed. Let's say this is the line joining their centers, and we have the sphere placed here. So they may be labeled as sphere A and sphere B. They are charged spheres, as they often are given in the questions. They are provided with certain charge, and as a result, they have an electric field around them. So due to the presence of charge on this, and due to the charge present on this sphere, they have electric fields, and they have their values of potential around the space about these charges. If I start from the center of this sphere and move to the center of this, the variation of electric field may be given with the help of a curve. If I start from the center of it, initially the electric field should be 0. And this is an important fact that you have already learned in the previous discussions, that electric field inside a charged sphere is always 0. As soon as you arrive at the surface of it, the electric field rises to its maximum value. Let's say this is the maximum value of it. You can go even higher on this graph, because the idea is just to show the location of the graph here. But in fact, the values of electric field may be any value depending upon the scale that you have chosen on this side. So on this scale, we have an electric field. Let's say it is reaching a certain value after you make that calculations and take that value here. Then you continue away from the surface of this charge, the electric field decreases in this manner. And at a certain location in between these two, let's say it is this location where the electric field is 0. And after this, the electric field increases again, and it becomes large here. And it is this point where it should have a large value. In fact, this should be like this. So a very large field is expected here, and then if you continue inside this sphere, the field again is 0. Now, if I have the values of this axis expressed in centimeters, let's say this is x expressed in centimeters, I can interpret this graph and find out many things about this. For example, I can find out exactly what is the size of this sphere, what is the radius of this sphere or the diameter of the sphere. That simply is this value read from this graph. So whatever you have, this in centimeters is equal to the radius of this sphere. So if this scale shows that this is 2 centimeters, this is 4 centimeters, this is 6 centimeters, and this is 8 centimeters, this is let's say 10 centimeter, and this is 12. You have 10 here, you have 12 here. So on this scale, clearly I can easily see that this is approximately 1.8, maybe 1.6. If this scale is easily readable, you can find out the radius of this sphere. Similarly, you can find the radius of this sphere. I can also find out where exactly the two fields cancel. Obviously, this is the position which is exactly which is exactly 8 centimeters from the center of this sphere, where the two fields are cancelling each other, and this is the position where the field of this sphere is exactly equal and opposite to the field of this. This also means that even if they have never mentioned what is the charge on this, I mean the sign of this, is it positive or negative? Are the two charges alike or they are opposite signs? It can be easily inferred from this graph that this charge is positive because all the values of the electric fields are positive on this side, and this charge is also positive because if this positive, only then its field is opposite in direction to the field of this. So both charges must be positive, and they are exactly equal and opposite at this location where they are cancelling. Also, I can find out what is the maximum value of electric field if I start from this position to this position. That could be read from the values from this and from this. If I compare these two values and I find that this is larger in magnitude because this shows the electric field magnitude. So this is the position where the electric field is maximum. When we say electric field is maximum, we say that rate of change of potential is maximum there because electric field is rate of change of potential there. And this brings us to another important idea, and that is, what if they ask us to show the variation of potential in the same space in between these two charges? Let me extend these axes and try to show you how the potential varies in between these two spheres. On the same scale, if this is 2, if this is 4, and this is 6, and this is 8, and this is 10, and this is 12 centimeter, in between the two spheres, the potential between the two, if this is the axis showing potential now, so therefore it is phi, and this is joule per coulomb, its unit. If electric field is 0 inside the sphere, that means rate of potential is 0. So rate of potential is only 0 if potential is constant. So it must be a value, sorry, it should be up to this. So if this is 2 and before 2 it finishes, I mean its radius is less than 2, the potential will remain constant up to the same point up to which the electric field was 0. So if electric field is 0 up to, let's say, 1.8 or 1.6 centimeter on this scale, potential is constant for exactly the same distance. But what happens after you go beyond that? Potential decreases, but it is not going to 0 like this, because although electric fields cancel, because they are opposite in direction, there is no problem with the potential in this case, because potentials of the two are positive. So although potential of this will decrease as you go away from it, potential of this, it's also positive, will also decrease as you go from away from this, but they will have some value and they add up and they will be minimum at this position. So this curve will be having its lowest value where the electric field was 0. But potential is not becoming 0 because this will have some positive potential at this position and this charge will also have some positive potential at this position. What happens to the potential after it? As you move closer to this, potential starts increasing again and it will rise to a large value, and since the rate of change of potential is very large here, electric field is very large here, that means the rate of change of potential means the gradient of this is large, and that we go like this, and then for exactly the same space where the E is 0, electric potential is constant like this. So in this space where E was 0, E was 0, phi is constant. So you have a curve like this. So the value of potential becomes large as you approach this sphere, and then as you go inside this sphere, the value of potential becomes constant. So the value of potential is constant inside this sphere, although electric field is 0. So you need to understand this relation. Electric field is 0 means rate of change of potential is rate of change of potential is 0 there. That means potential is constant. That is why its rate of change with distance is taken 0. So potential is constant here, potential is constant here, potential is minimum here where electric field was 0. So you have a dip here in between the two spheres. So this is the kind of graph. Sometimes they ask us to draw a graph like this, although most of the questions have this graph already drawn and you just have to interpret this variation the way we have discussed it. So these are various questions. How is force related to the gradient? How is electric field related to gradient? That is already discussed, but let me remind you, delta phi, if this is the potential, its rate of change with the distance, which is the gradient of potential. This is always E. If I talk about only magnitudes, ignoring the signs, that means if you take the gradient of potential and you multiply it by the charge involved, that becomes the force. That simply means that if instead of potential, you have a graph of potential energy, which will be similar shape, then it will be Q delta phi. So in that case, it will be rate of change of the gradient in that case will be force. So if this is E, then QE will be delta, which is Q, and this is rate of change of, so that means force. If you multiply both sides by Q, this part, which is electric field, let's say instead of potential, you have a quantity which is called potential energy. In that case, it will be joules. So joule varying, let's say in this manner, then it will be the rate of change of U. Let's say this quantity is U now, which is potential energy. So rate of change of potential energy is force. So this is also a part of various questions, because instead of potential varying, you are studying the potential energy varying. Now if you take the gradient of it, the rate of change of it, the quantity is not electric field, it is force. So I hope you understood the idea. Let's move on to another question that I have selected for discussion. I hope those questions in which graphs are involved, and there are so many questions like this, at least you can attempt those questions on your own now. One question which is particularly challenging also involves two charges placed at a certain distance apart, and they are labeled as charge A and charge B. This is A, this is B, and they are exactly 12 micrometer apart. Both are positive and their magnitudes are given. One is 6.4 into 10 raised to power minus 19 coulomb. And similarly, this is 6.4 into 10 raised to power minus 19 coulomb. So identical charges placed side by side at a distance that is known. There is one point labeled P. This is exactly 3 micrometer apart. And there is a point Q here. This is labeled point P. This is labeled Q. And it is also exactly 3 micrometer apart. Its distance from this charge is also 3 micrometer. So this charge, which has this magnitude and the same magnitude of this charge, they are placed 12 micrometer apart, and at 3 micrometer from this charge, we have a point P, and at the same distance from this charge, we have a point Q. The question is, what if I start exactly from the center and move an electron from this to this position? So we want to calculate the work done when an electron moves from the center of the line AB to the point P. From the center to the point P. So this is the question. This involves many calculations before you calculate this work. But the main idea is, if I know the difference of potential between these 2 points and multiply by the charge of an electron, I can calculate the work involved. So Q delta V is equal to work. This is the equation that you learned in the AS, if you remember. If you multiply the charge of a charged particle by the difference of potential, this is the work that the field does on the charged particle to accelerate it, or if the object is moving and the field does force force in the opposite direction, it decelerates it and brings it to rest. So either way, this is the work on the charged particle. In this case, maybe if you leave this electron here, it moves on its own to this, or it may be a work that we have to do in order to push the electron from this to this. It depends on the repulsive forces or attractive forces involved. That may be a question that you may answer if you carefully understand the situation. But here we just have to calculate the work involved. So the basic idea is to calculate the difference of potential between this point, which we have labeled as the center of the line AB basically. So the first thing is to calculate the potential here due to both the charge at A and the charge at B. So potential at A, let's say I label it as VA. VA is the total potential at the potential due to this particle at the center plus VB. So at the center we have two values of potential, one due to the charge at A and one due to charge at B. So we add these two, K Q over R, and since these values happen to be same for the two cases, K is common already, Q is same for the two, and it is at the same distance as this charge. So this R is also same for the two. So this is simply multiplied by 2. So the two charges, because they are same, are having the same potential at the center because the distance is also same. So when you use all these values, K is 9 into 10 raised to power 9, Q, which is same in the two cases, 6.4 into 10 raised to power minus 19, and R is also same. This is exactly 6 because 12 is the total. So 6 into 10 raised to power minus 6 meters. So if you simplify this, you get a number which I calculated to be 1.92 into 10 raised to power minus 3. So this is potential at the center due to the two. So this is joule per coulomb. So this is one number. Now what is the potential at B? A similar exercise is for the potential at B. Again, VA at P plus potential due to B. So this is at center and this is at point P. At point P now, you have potential due to this, which is VA again, and potential due to this at this P due to the charge at B. So this time, this is KQ over R. Now R will be different in the two. So KQ is taken common because that is same for the two, and 1 over, this is exactly 3 micrometer apart, minus 6, plus 1 over, this is now 9 micrometer from this, because you have moved to this point. So P is, the total distance is 9 into 10 is power minus 6 meter. This is the number that we have to simplify. K is already known, Q is already known, and this is to be simplified. And this number I found to be 2.56. Let me write on this side so you can read it clearly. I think I should write here now, removing this, so you can clearly read the values. At P now, the total potential at P due to the two charges is KQ over R1 plus KQ over R2, because R1 is this distance, R2 is this. KQ is same for the two, 1 over 3 into 10 is power minus 6 plus 1 over 9 into 10 is power minus 6 meters. So when you simplify this using these values known, it comes out to be 2.56. 2.56 into 10 is power minus 3 joule per coulomb. So it was, at the center, it was 1.92 into 10 is power minus 3, and now that you have moved to this point, it is this. So difference of potential is therefore 2.56 minus 1.92 into 10 is power minus 3 joule per coulomb. This is delta V. So if we calculate this number, it comes out to be, I mean the difference, this is 0.64. 0.64 into 10 to the power minus 3 joule per coulomb. This number is to be multiplied by the charge on electron if we want to calculate the work done if an electron is moving from this to this point. So difference of potential multiplied by charge, it gives us, if I use this value here and charge on electron, which is the elementary charge, we multiply this and we get the number 1.0 into 10 is power minus 22 joule of work is done. So this is the kind of calculations in this questions. And you have many questions of this type in which you have two charges placed side by side, and the space in between, you have a charged particle moving from one position to the other. So this is how you handle it. Let's move on to the last question, and with that we'll complete our discussion for today. The last question is again one typical example of various questions of this type in which you place a certain charge at a position in space and you fire an electron, fire an alpha particle or any other smaller charge towards that bigger charge, a bigger sphere if it is charged. And you have to calculate what happens to it, whether this will be able to reach it, with what speed we have to send it to that charge if we want the two to hit. This is the kind of question, and you have many questions of this type in the exam. This is a charged particle, and for this charged particle, they have given us the value of specific charge. Specific charge means charge to mass ratio. This is known as charge to mass ratio, and they call it specific charge of any particle, and its value is given to be 9.58 into 10 raised to power 7 coulomb per kilogram. This charged particle is moving with a speed of 2.5 into 10 raised to power 5 meter per second. And we have a large sphere which is positively charged. It is given positive charge on its surface, and as a result it has developed a potential of 470 volt. That is the potential at the surface of this charged sphere. Now this particle is sent to this with this speed, and we want to know whether this charged particle will be able to reach this charge or not, at least touch that surface or not. So what formula should we use for that purpose? Obviously, this is the kinetic energy of this particle that is converted to potential energy, because both of these are positive. This is the first thing that you will understand from the situation, because they have shown it to be positive. So this is a positive charge moving. This is also positive. So it will be repelled. It slows down, and maybe before it touches it, it comes to rest for a moment, and then it is repelled. So our calculations that we are going to do now, they will show whether it will be able to reach the surface before it comes to rest or not. So the first thing is, what is this kinetic energy equal to in terms of charges and potentials? So this is again QV. So all the kinetic energy is converted to its potential energy at a certain position, and let's say that position is the surface of it or before it happens. If I simplify it, we have an expression for the velocity. This is potential, this is capital V, and the small v is the value of velocity with which it is moving. So this V, the velocity, it will be 2q capital V divided by m, and all this under root. If I put all these values, 2 multiplied by q over m, this is q over m. I have written E here. Usually E is the symbol for charge, but Q could also be written here. So let me make it Q over M to avoid any confusion. So Q over M, which we know is 9.58 into 10 raised to the power 7. This V is also known, and that is 470 volt. This all is under root. When I calculate this, the answer I get is 3 into 10 raised to the power 5 meter per second. Now, what does this mean? This means that if I'm using this value of potential, that means I'm trying to find the speed of this, which should be there if this particle is to reach exactly the surface. Now this speed comes out to be greater than 2.5 into 10 raised to the power 5. That means this particle has not large enough speed, so it won't be able to reach the surface. It will stop earlier than this, then it will be repelled back, coming to rest for a moment. So this is the last question I selected for discussion today. We may have a few more questions for discussion like this in the next lesson. Thank you for today.